just start here. Oops. Cancel, please. Alright, what are we doing here? Check. Let's say 12:30 to 1:30 today for our lunch cardio, because I'm doing shorter cardio sessions. And then this can just be 1:30 to 5. Oh, PM. Okay. So, we're trying to complete the entire course by Sunday. Seems like a lot, but I'm focusing and I'm cutting scope on this course to where I just need to get through the lectures, the recitations, this last chapter of reading, and maybe a few labs if we have time. But Sunday is going to be my cutoff date for this course. Not going to be taking any of the exams, the midterms, or anything. My objective is to get breadth on these topics, and I'm getting a lot of freaking breadth and depth on these topics. Probably too much depth. There's so much more I want to learn about. So just looking in front of me, I have Ghidra for reverse engineering compilers. I got the Dragon book. I got the ML compiler book. Algorithms, BPF performance tools, systems performance, learning BPF, C++ concurrency in action, systems design, data science, operating systems, 3 easy pieces, programming massive parallel processors, CUDA by example, how to prove it, mathematics, the binary analysis book that I'm currently reading. There's like so much stuff that I want to like cover this year. Like I don't feel like going further into the depth of this book is going to provide me the opportunity to get the breadth that I want. I feel like I've learned a lot reading this book, and I could spend a lot of time getting every little morsel of knowledge out of it and feeling really comfortable operating on this layer of computing. But my intention in reading this book was to get exposure to this layer of computing, appreciate it, get some experience, but not spend my entire career here. I want to learn more mathematics. I want to learn more C++. I want to learn more parallel computing, CUDA. I want to learn more about SIMD. I want to learn about compilers, parsing techniques, semantic analysis, like all that stuff. I'm not going to have time for that in my learning schedule if I spend too much time focusing on the depth that this book can provide. So it's a trade-off. And I have this new perspective because of Richard Feynman and his technique of basically like focusing on areas that he needs when he needs it. It's kind of like a just-in-time learning approach. And reading this book cover to cover and going in depth incrementally throughout the entire thing, doing all the homework problems, doing all the practice problems, doing all the labs, and just working your way through it. You could spend an entire year on this book and this problem domain. And that's more like pre-compiling your program, which has its place for sure. But I feel like I want to pre-compile enough knowledge of these areas of computing and then page in just in time compile the stuff that I need when I need it. I guess it's different between eager and lazy, and I think demonstrably lazy is better than being eager. When you have so much you want to accomplish learning wise and only a finite amount of time on this planet. So that's where I'm at with everything. What is this book over here? I forget what this one is. Oh, the TCP/IP Illustrated. I haven't even cracked that one open. That was not on the agenda for this year, so I have a different pile for the books that I had to cut for cutting scope for the year. Anyway, so the objective is to get everything done by Sunday. So let's get into it. So we left off here, I believe. We're skipping over the 9.5. If we go to chapter 9 problems, we got a skip notation there. Okay, so dynamic memory allocation. This is where we left off. We did one lecture on this. I think there's 2 lectures. And this takes us, it's going to be 25, 35. Pretty much it's going to be about 35 pages today of reading. And then we're done with reading. So dynamic memory allocation. While it is certainly possible to use the low-level mmap and munmap functions to create and delete areas of virtual memory, C programmers typically find it more convenient and more portable to use a dynamic memory allocator when they need to acquire additional virtual memory at runtime. So he does talk about sbreak and dynamic memory allocators. I'm curious, like I'm just going to write a program here, or I'll have AI do it for me. Write a C program that allocates memory dynamically in a loop of various sizes to test what syscalls are made using strace by the memory by the libc. Okay, that'll give me that code. I go over here, jump over to what were we? CSAPP CD chapter 09, and then this will give us a little program here. That's quite a large program for the test that I want to do. Let's bump this up here. We'll just say vim test allocator .c, and we'll look over it here. Okay, so it blocks on getchar, and then you press enter, or any character for that matter. And then it does small allocations for number of iterations. We're going to say, hey, size t is that. We're going to malloc it up into our ptr iters. If anything errors out, then we exit 1. Otherwise, we do a memset into there of a single char, and small will be 64 KB, 128 KB, 4 megabytes. Okay, so that's going to be, say, hey, char up to size, and then at the end here, we're just going to free everything. So phase 2, large allocations, likely mmap. So we do that. I don't like this. I don't like this stuff here. Phase 3, mixed allocations. So we do large min and large max. This thing just goes random between large min and large max. And then phase 3, we introduce small and large and free it, and then we just print out done, which you don't need. Okay, let's do make. We don't have a make file, so CP. What do we got here? Chapter 7, make file. To here, vim make file. We can clean up this a little bit. Program binaries. Okay. Don't need any of the library code. All program. Okay, we need a better makefile here. No. CP chapter 06 makefile. No makefile there. 5 makefile. Okay. There we go. Okay. Clean program binaries. We're using zigcc. Looks good. Let's do a make on it, and then we run build. Oh, we need the get ignore too. Dot get ignore. Let's run build. Oops. Let's do strace on. Sorry, strace break and mmap and m unmap. I think that's it. On build test allocator. Yeah, okay. Valid system call sbreak. Man sbreak. Man 2 sbreak. It's definitely a syscall. SBRK. Well, here it says break. I guess I want to say, hey, is sbreak a real syscall, or does it just map to break on AMD 64 Linux? Come on, Sam Altman. All right. And then there's madvise too. Madvise. Yeah, there's no sbreak. Okay. Okay. Let's take a look here. I'm just gonna pipe that into out.txt, and of course it's on standard error, so we need to say, hey, send 2 to 1. I think this has to be at the end, maybe? There we go. Vim out.txt. And then this should interleave all of our standard out as well, right? Why didn't we get any of that? Maybe I didn't have that in the test allocator.c. I thought I did. We print out the PID. And we'll say starting small allocations. Okay. I need semicolons on all these. Space to go, we don't need that. Okay. Then down here we'll say starting larger allocations. Might as well put the %d in here, right? %d, and then this will be size. Kind of like that better, so we can see the actual sizes. Okay, and then starting larger allocations, and here we'll say starting mixed allocations. And then up here, we also need to have like a free here. Free. And instead of size, we're just going to say I. Or maybe we'll say PTRs of I and give it the P. Minus here. And we'll just search for free. Okay. Get status get or make. No, rerun our thing here. Vim out.txt. Okay. 14,000 lines. Not going to be reviewing all that. So this is just stuff to set up the process itself. What's funny is I don't see the standard out at all here. Oh, it did a bunch of breaks here to do some type of allocation before this even started. Interesting. Did that actually happen, or is it lying? Malbrook? Seems like we might not be interleaving these events correctly. But we get break, set, lock, malloc. Okay. Lots of breaks. These old batches of breaks. So all those are breaks, and then we free everything. And then we start M mapping stuff. So it's a mixture of things. These largers are all M maps, it looks like, an M unmap. And then the last group should be after the freeze. Starting mixed allocations. Mixed allocation is break. Break. Was there any M maps in there? Let's go up, let's search for starting. Small, large, mixed. Here, now I'm going to search for M map. Sorry, let's go back to mixed. Sorry, starting. Starting. Mixed, which is 10,178. And let's search from here for M map. We do have some M maps, or a map. Huh. Interesting behavior. Let's read a little bit more about. Usually break calls when the heap grows. What is this? TTTE man s trace. It's saying, hey, do it with -f, which is follow. Forks, which you don't really need. TT, which is absolute timestamps. Precision is microseconds. And then T, this is called times. Oh, you can say trace memory. Interesting. Okay. Let's try that. Oops, quit please. Wonder if this thing fixes the interleaving issues that we have currently. Doesn't appear like it does. All right. madvise. madvise is not used. So why is it that the default libc allocator uses Burk for small allocations and mmap for larger versus just picking one strategy for both? No per allocation kernel involvement once space is reserved. That's not how that works, bro. I don't like this format. Alright, let's continue reading. We didn't get very far. This is what happens when I drink caffeine, is that my brain just goes like super deep on things and explores things instead of like making progress on things. I just go down different rabbit holes. So I learned a little bit about J. Malloch there, mainly adopted in dynamically typed languages, which is where I've seen it mostly used, is in Ruby and Python, that type of thing. Adopted by Mozilla Firefox, Mozilla Organization, and Meta. Supposed to be used primarily for its advantages in minimizing lock contention in highly concurrent threaded applications. Yeah, I guess, it's an option for a memory allocator, but I couldn't tell you immediately off the top of my head what the design decisions and trade-offs were in its design. The other thing we learned is the default libc allocator uses both break and mmap, which my limited experience with allocators, I've seen allocators that use exclusively break, and I've seen allocators that use exclusively mmap. This is the first example of an allocator that I've seen that uses both break and mmap. And we learned a little bit of the history why that is the case with glibc. All right, so let's continue on reading. So while it's certainly possible to use the low-level mmap and mmap functions to create and delete areas of virtual memory, C programs typically find it more convenient and more portable to use a dynamic memory allocator when they need to acquire additional virtual memory at runtime. A dynamic memory allocator maintains an area of a process's virtual memory known as the heap. Details vary from system to system, but without a loss of generality, we'll assume that the heap is an area of demand zero memory that begins immediately after the uninitialized data area. It grows upward towards the higher addresses. For each process, the kernel maintains a variable break, pronounced break, that points to the top of the heap. An allocator maintains the heap as a collection of various sized blocks. Each block is a contiguous chunk of virtual memory that is either allocated or free. An allocated block has been explicitly reserved for use by the application. A free block is available to be allocated. A free block remains free until it is explicitly allocated by the application. An allocated block remains allocated until it's freed, either explicitly by the application or implicitly by a memory allocator itself. Allocators come in two basic styles. Both styles require the application to explicitly allocate blocks. They differ about which entity is responsible for freeing allocated blocks. Explicit allocators require the application to explicitly free any allocated blocks. For example, the C standard library provides an explicit allocator called the malloc package. C programs allocate a block by calling the malloc function and free a block by calling the free function. The new and delete calls in C++ are comparable. But in C++, I don't think you have to delete. In C++, do you have to call delete on heap allocated memory, or does the scope variable falling out of scope call delete for you? Okay. Yeah, resource acquisition is initialization. So you use the unique pointer, and it automatically gets deleted when it falls out of scope. Well, that's a fucking global, so you'd never delete that thing. Don't have to think about it. I feel like you should think about everything in your software that you build. You shouldn't just say, oh, I don't have to think about things. That's stupidity. All right. Implicit allocators, on the other hand, require an allocator to detect when an allocated block is no longer being used by the program and then free the block. Implicit allocators are also known as garbage collectors, and the process of automatically freeing unused allocated blocks is known as garbage collection. For example, higher level languages such as Lisp, ML, and Java rely on garbage collection to free allocated blocks. The remainder of this section discusses the design and implementation of explicit allocators. We will discuss implicit allocators in section 910. For concreteness, our discussion focuses on allocators that manage heap memory. However, you should be aware that memory allocation is a general idea that arises in a variety of contexts. For example, applications that do intensive manipulation of graphs will often use the standard allocator to acquire a large block of virtual memory, and then use the application-specific allocator to manage the memory within that block as the nodes of the graph are created and destroyed. The malloc and free functions. C standard library provides an explicit allocator known as malloc package. Programs allocate blocks from the heap by calling malloc function. It's in standard lib. Pretty straightforward. You already know this. Hey, there's an aside. How big is a word? Recall that our discussion of machine code in chapter 3 that Intel refers to 4-byte objects as a double words. However, throughout this section, we will assume that words are 4 bytes. Yeah, because a quad word would be 64 bits, 8 bytes. A double word would be 4 bytes or 32 bits. A word would be 16 bits or 2 bytes. And then you have a char, which is a half word, I guess, according to assembly machine instructions. Double words are 8 bytes, which is consistent with conventional terminology. Okay. The malloc function returns a pointer to a block of memory that is at least size bytes that is suitably aligned for any kind of data object that might be contained in the block. In practice, alignment depends on whether the code is compiled to run in 32-bit mode or 64-bit mode, the default. In 32-bit mode, malloc returns a block whose address is always a multiple of 8. In 64-bit mode, that address is always a multiple of 16. So what I want to do is look at the memory allocator that I implemented in KNRC and see if I had the right alignment. So I'm just going to bust open a browser window here and go to KNRC. If I still have this, yeah. Still in my history. And then I think it's chapter 8, allocator.c. So here we had some alignment stuff that we did. This type def. Oh, we had to write to standard error because, yeah. Okay, so header alignment type is max align t. Header alignment is a line of header alignment type, max align t. And we get that from probably standard def or maybe standard lib, probably standard def though. So header alignment type. So do a line of max align t. And then we use that, say align as max align t. This is a 0-byte field that serves two purposes. It forces the alignment of the header to the maximum value, so callers get a starting address that is aligned to whatever type they use. Using the FAM allows, so this is a this is the syntax here. I forget what they call this thing though. CFAM. Flexible array members. Allows us to easily reference the memory after the header, which is where the requested allocated memory starts. Obviously, use with caution, as dealing with characters beyond the header when there are none could result in chaos. Note this asserts that both the size and alignment of the header are equal to the max alignment. So I'm kind of curious what a line of this max align t is. So let's get out of here and say clang REPL, and we're going to pound include standard def.h. Is that a thing? And then max align t, and we're gonna have to pound include standard lib standard io.h. Let me delete all this. Boop, 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 boop. Printf out new line %d a line of max align t is equal to that. A line of max align t. Okay, LZ. Oh yeah, Z because size, and then U unsigned. So yeah, it is 16, which is what they said in the book. Yep, cool. Just wanted to double check on that. Okay, if malloc encounters a problem, e.g. the program requests a block of memory that is larger than the available virtual memory, then it returns null and sets error no. Malloc does not initialize the memory it returns. Applications that want Initialized dynamic memory can use calloc, a thin wrapper around malloc function that initializes the allocated memory to 0. Applications that want to change the size of a previously allocated block can use the realloc function. Dynamic memory allocators such as malloc can allocate or deallocate heap memory explicitly by using the mmap and munmap functions, or they can use sbreak function or break. The sbreak function grows or shrinks the heap by adding increment to the kernel's break pointer. If successful, it returns the old value of break, otherwise it returns -1 and sets error node to E no mem. If incr is 0, then sbreak returns the current value of break. Calling sbreak with a negative increment is legal but tricky because the return value, the old value of break, points to abs incr bytes past the new top of the heap. Programs free allocated heap blocks by calling the free function. The pointer argument must point to the beginning of the allocated block that was obtained from malloc, calloc, or realloc. If not, then the behavior of free is undefined. Even worse, since it returns nothing, free gives no indication to the application that something was wrong. As we shall see in section 911, this can produce some baffling runtime errors. Baffling! Okay, figure 934, allocating and freeing blocks with malloc and free. Each square corresponds to a word. Each heavy rectangle corresponds to a block. Allocated blocks are shaded. It's hard for me to see the colors here, but allocated blocks are shaded. Padded regions of allocated blocks are shaded with a darker blue. Free blocks are unshaded. Heap address increases from left to right. So, yeah, pretty straightforward. So we call malloc with 4 times size of int, which will give us P1. And then we do P2 with 5 times. Then we have some padding on that to get it aligned properly. We call another malloc. Then we call free on that, which gives us back all that space. And then we call another malloc. Makes sense. Okay, 934 shows how an implementation of malloc and free might manage a very small heap of 16 words for a C program. Each box represents a 4-byte word. The heavy lined rectangles correspond to allocated blocks shaded and free blocks unshaded. Initially, the heap consists of a single 16-word double word aligned free block. Throughout this section, we will assume that the allocator returns blocks aligned to 8-byte double word boundaries. Figure 934A, the program asks for a 4-word block. Malloc responds by carving out 4-word block from the front of the free block and returning a pointer to the first word of the block. B, the program requests a 5-word block. Malloc corresponds by allocating a 6-word block from the front of the free block. In this example, malloc pads the block with an extra word in order to keep the free block aligned with a double word boundary. C, the program requests a 6-word block and malloc responds by carving out a 6-word block from the free block. The program frees the 6-word block that is allocated in figure B. Notice that the call to free returns a pointer to P2. Pointer to P2 still uses the free block. It is the responsibility of the application not to use P2 again until it's reinitialized by a new call to malloc. The program requests a 2-word block. In this case, malloc allocates a portion of the block that was freed in the previous step and returns a pointer to this new block. So if we are 16 bytes aligned in like a normal AMD 64 situation, then that would give us the low order bits. So we have the first bit would be always 0, 4, 8, 16. well, let's just do some math here. Because I have a hard time visualizing this. Python. So we have two, or we'll just say 16 here. And we'll do bin of that. So we have four bits, all zeros, times 2 here. Still 4 bits, all zeros, times 3, times 4, times 5. So you always have those 4 bits as zeros, even when it's 7. 4 bits, zeros. So those 4 bits, if you're allocating in blocks of 16, those 4 bits are kind of like meaningless. They're always 0, which means that you can use them for something else. You can assume they're 0 and use the actual storage in the memory for something else, which is what we'll see later in this chapter. Kind of skipping ahead a little bit because I know it's coming. Why is this thing not killing us? Okay, good. Okay, why dynamic memory allocation? The most important reason that programs use dynamic memory allocation is that often they do not know the sizes of certain data structures until a program actually runs. For example, suppose we are asked to write a C program that reads a list of n ASCII integers, 1 per line from standard in into a C array. The input consists of an integer n, followed by the n integers to be read and stored into the array. A simple approach is to define an array statically with some hard-coded maximum array size. Allocating arrays with hard-coded sizes like this is often a bad idea. So if you look at the code here, they just have a pound define max n. That's obviously compile time constant. 15213, and if n is ever greater than that, then we error out. So not only is it suboptimal in that you're limiting the maximum amount of input you can provide, the program will just not function, but also you're requiring that even with situations we have small amounts of input, that the program use more memory than it otherwise would need. The value of max n is arbitrary and has no relation to the actual amount of available virtual memory on the machine. Further, if the user of this program wanted to read a file that was larger than max n, the only recourse would be to recompile the program with a larger value of max n. While not a problem for the simple example, the presence of hard-coded array bounds can become a maintenance nightmare for large software products with millions of lines of code and numerous users. A better approach is to allocate the array dynamically at runtime after the value of n becomes known. With this approach, the maximum size of the array is limited only by the amount of available virtual memory. Boop. So here we read in our n, and then we malloc up n times size of int, and that's n, we free it. Dynamic memory allocation is a useful and important programming technique. However, in order to use allocators correctly and efficiently, programmers need to have an understanding of how they work. We will discuss some of the gruesome errors that can result from the improper use of allocators in section 911. I'm looking forward to that section. Appropriately, it's section 911. That's a bad joke. I shouldn't have said that. But it is a catastrophe when your memory gets messed up. Anyways, allocators, requirements, and goals. Explicit allocators must operate within some rather stringent constraints. Handling arbitrary request sequences, making immediate responses to let's just start from the beginning here. I don't want to read ahead too much. So explicit allocators. So these are things that must free. You must new up, and you must malloc, and you must free, or calloc, or whatever. So explicit allocators must operate within rather stringent constraints. Handling arbitrary request sequences. An application can make an arbitrary sequence of allocate and free requests subject to the constraint that each free request must correspond to a currently allocated block obtained from a previous allocate request. Thus, the allocator cannot make any assumptions about the ordering of allocate and free requests. For example, the allocator cannot assume that all allocate requests are accompanied by a matching free request, or that matching allocate and free requests are nested. Yeah, makes sense. Making immediate responses to requests. The allocator must respond immediately to allocate requests. Thus, the allocator is not allowed to reorder or buffer requests in order to improve performance. Using only the heap, in order for the allocator to be scalable, any non-scalar data structures used by the allocator must be stored in the heap itself. Aligning blocks, alignment requirement. The allocator must align blocks in such a way that they can hold any type of data object. Not modifying allocated blocks. Allocators can only manipulate or change free blocks. In particular, they are not allowed to modify or move blocks once they are allocated. Thus, techniques such as compaction of allocated blocks are not permitted. You can only do that for free blocks. Working within these constraints, the author of an allocator attempts to meet the often conflicting performance goals of maximizing throughput and memory utilization. So there's two metrics here. So it's throughput and memory utilization. Throughput of requests and how well they're packed. Goal 1, maximizing throughput. Given some sequence of n allocate and free requests, we would like to maximize an allocator's throughput, which is defined as the number of requests it can complete per unit time. For example, if an allocator completes 500 allocation requests and 500 free requests in 1 second, then its throughput is 1,000 operations per second. In general, we can maximize throughput by minimizing the average time to satisfy allocate and free requests. As we'll see, it is not too difficult to develop allocators with reasonably good performance, where the worst case running time of an allocate request is linear and the number of free blocks and the runtime of the free request is constant. I mean, you can implement an allocator that has constant time for allocations and frees using mmap. I mean, mmap's going to be constant time. It's just not going to be very performant. But asymptotically, it's a constant. You're just making a syscall. And unless it might be O of n, to be honest, because the kernel might have to traverse the virtual page mappings or whatever they call them. I forget the name of it. But basically the memory mappings. And I believe, according to the book, that's a linked list, which would be O of n. Traversal. So yeah, that might slow things down a bit with the syscall, so it might scale linearly. Maybe that's what they're talking about. Okay, maximizing memory utilization. Naive programs often incorrectly assume that virtual memory is an unlimited resource. In fact, the total amount of virtual memory allocated by all the processes in a system is limited by the amount of swap space on disk. Good programmers know that virtual memory is a finite resource that must be used efficiently. This is especially true for a dynamic memory allocator that might be asked to allocate and free large blocks of memory. There are a number of ways to characterize how efficiently an allocator uses the heap. In our experience, the most useful metric is peak utilization. As before, we are given some sequence of n allocate and free requests. If an application requests a block of p bytes, then the resulting allocated block has a payload of p bytes. After request r sub k has completed, let the aggregate payload denoted by p sub k be the sum of the payloads of the current allocated blocks, and let h sub k denote the current monotonically non-decreasing size of the heap. Then the peak utilization over the first k plus 1 request denoted by u sub k is given by u sub k, which utilization up to k plus 1 requests is the max of pi where I is less than K. So basically there's a max of the aggregate payload divided by H sub K. And if they're both equal, then it'd be 1. But most times H sub K is going to be greater, and it'll be less than 1, like greater than 0, less than 1 for the U sub K value. The objective of the allocator then is to maximize the peak utilization UN minus 1 over the entire sequence. As we will see, there is tension between maximizing throughput and utilization. In particular, it is easy to write an allocator that maximizes throughput at the expense of heap utilization. One of the interesting challenges in any allocator design is finding an appropriate balance between the two goals. Relaxing the monotonicity assumption. We could relax the monotonicity, non-decreasing assumption in our definition of U sub K and allow the heap to grow up and down by letting H sub K be a high watermark over the first K plus 1 requests. Why would you want to do high watermark? Because you're taking a max. I think that's why you want to do high watermark. Taking a max of the payloads. Yeah, that's why. All right, fragmentation. The primary cause of poor heap utilization is a phenomenon known as fragmentation, which occurs when otherwise unused memory is not available to satisfy allocate requests. There are two forms of fragmentation: internal fragmentation and external fragmentation. Internal fragmentation occurs when the allocated block is larger than the payload. This might happen for a number of reasons. For example, the implementation of an allocator might impose a minimum size of allocated block that is greater than some requested payload. Or, as we saw in figure 934b, the allocator might increase the block size in order to satisfy alignment constraints. Internal fragmentation is straightforward to quantify. It is simply the sum of the differences between the sizes of the allocated blocks and their payloads. Thus, at any point in time, the amount of internal fragmentation depends only on the pattern of previous requests and the allocator implementation. External fragmentation occurs when there is enough allocated free memory to satisfy an allocate request, but no single free block is large enough to handle the request. For example, if the request in figure 934E were for 8 words rather than 2 words, then the request could not be satisfied without requesting additional virtual memory from the kernel, even though there are 8 free words remaining in the heap. The problem arises because these 8 words are spread over 2 free blocks. External fragmentation is much more difficult to quantify than internal fragmentation because it depends not only on the pattern of previous requests and the allocator implication, but also on the pattern of future requests. For example, suppose that after K request, all of the free blocks are exactly 4 words in size. Does this heap suffer from external fragmentation? The answer depends on the pattern of future requests. If all of the future allocate requests are for blocks that are smaller than or equal to 4 words, then there is no external fragmentation. On the other hand, if one or more requests ask for blocks larger than 4 words, then the heap does suffer from external fragmentation. Since external fragmentation is difficult to quantify and impossible to predict, allocators typically employ heuristics to attempt to maintain small numbers of larger free blocks rather than large numbers of smaller free blocks. So we got implementation issues, implicit free lists, placing allocated blocks, splitting free blocks, getting additional heap memory, coalescing free blocks, coalescing with boundary tags. And then we got our practice problem, putting it together, implementing a simple allocator. General allocator design, basic constants and macros for manipulating a free list, creating an initial free list, freeing and coalescing blocks, allocating blocks, some practice problems at the end there. And then we get into explicit free lists, segregated free lists, more practice problems, and finally we get into garbage collection. So most of the remaining part of this chapter is on just implementation of dynamic memory allocators, free lists, stuff like that. And then we get into garbage collection, which is a very short coverage of the topic, maybe a couple pages. And then we get into common memory related bugs in C programs, which I'm looking forward to. And that's it. So most of this chapter that remains the dynamic memory allocator stuff. Okay, so we talked about the two different types of fragmentation, external and internal fragmentation. And internal makes a lot of sense to me. It's very easy to measure, and it makes sense why you'd want to optimize for reducing internal fragmentation. External fragmentation seems harder to measure, dependent on future events that you don't know what they're going to be, and overall seems less useful. I mean, you can just have a heuristic like you're saying, where you just reduce the amount of small fragmented blocks of memory. Okay, implementation issues. The simplest imaginable allocator would organize a heap as a large array of bytes and a pointer p that initially points to the first byte of the array. To allocate size bytes, malloc would save the current value of p on the stack, increment p by size, and return the old value of p to the caller. Free would simply return to the caller without doing anything. This naive allocator is an extreme point in the design space, since each malloc and free execute only a handful of instructions. Throughput would be extremely good. However, since the allocator never reuses any blocks, memory utilization would be extremely bad. A practical allocator that strikes a better balance between throughput and utilization must consider the following issues. Free block organization. How do we keep track of free blocks? Placement. How do we choose an appropriate free block in which to place a newly allocated block? Splitting. After we place a newly allocated block in some free block, what do we do with the remainder of the free block? Coalescing. What do we do with a block that has just been freed? The rest of the section looks at these issues in more detail. Since the basic techniques of placement, splitting, and coalescing cut across many different free block organizations, we will introduce them in the context of a simple free block organization known as an implicit free list. I like this implicit free list. It's like very simple. One block, or you'd say one word header. Which shows a block size. Oh, damn. Let's go back to Clang REPL, and we're going to pull in this standard IO, printf out. Which is going to be %d, and I want to give it size of size t, which I think size t is going to be 8. Yeah, it's 8. All right. Let's go to README. Let's mark our progress here. Otherwise, I'm going to feel demotivated. So we're on implementation issues, implicit free list. We're on here. Okay. If we go over here, we got about hour and 45 before lunch. And we're about an hour-ish, hour 45 in. Something like that. No, it's an hour and a half. Yeah, it's hour 45 and we're about an hour 15 in, I guess. Okay, let's continue reading. Implicit free list. Any practical allocator needs some data structure that allows it to distinguish block boundaries and to distinguish between allocated and free blocks. Most allocators embed this information in the blocks themselves. One simple approach is shown in figure 935, format of a simple heap block. In this case, a block consists of a one-word header, the payload, and possibly some additional padding. The header encodes the block size, including the header and any padding, as well as whether the block is allocated or free. If we impose a double word alignment constraint, then the block size is always a multiple of 8, and the 3 low-order bits of the block size are always 0. Thus, we need to store only the 29 high-order bits of the block size, freeing the remaining 3 bits to encode other information. In this case, we are using the least significant of these bits, the allocate bit, to indicate whether the block is allocated or free. Okay, let's take a look at this diagram. Bit 0 is allocated if it's 1, free if it's 0. Something just occurred to me that I wanted to follow up on. I am aware of some techniques to use unused bits in the virtual address of pointers to do some check summing crypto to verify pointers pointing to correct locations to prevent some exploits. What is this called? Pointer authentication. Use on ARM. Cryptographic signature is stored in unused high bits of the pointer. On dereference or use, the CPU verifies the signature. This is formally known as pointer authentication codes. Protects against things like return address corruption, function pointer hijacking, return-oriented programming. Let's see. ROP is return-oriented programming. What is JOP? Tag pointers, more general concept. Use unused bits, often high bits on a 64-bit system or low alignment bits to store metadata. Yeah, that's what we're doing right now. Using the low alignment bits. Not always cryptographic can be. GC state and runtimes, type info flags, security variants of this ID overlap with PAC. Pointer authentication codes, memory tagging. I've heard of this, but I'm not familiar with it. CHERI. Indirect jumps, jump-oriented programming. Unconditional jumps. Okay. Next page. Boop. I did want to check in on this capability hardware enhanced risk instructions. Is a technology designed to improve security for reduced instruction set computer processors. Cherry aims to address the root cause of problems caused by lack of memory safety in common implementations of programming languages such as C and C++, which are responsible for around 70% of security vulnerabilities in modern systems. The hardware works by giving each reference to a piece of data or a system resource its own access rules. This prevents programs from accessing or changing things they should not. It also makes it hard to trick a part of a program into accessing or changing something that should be able to access, but at a different time. The same mechanism is used to implement privilege separation, dividing processes into compartments that limit the damage that a bug, security, or otherwise can do. Cherry can be added to many different instruction set architectures, including MIPS, ARM64, RISC-V, making it usable across a wide range of platforms. Software must be recompiled to gain fine-grained memory safety benefits from Cherry, but most software requires few, if any, changes to the source code. Cherry's importance has been recognized by governments as a way to improve cybersecurity and protect critical systems. It is under active development by various businesses and academic organizations. This sounds similar to me to Phil C. Just from a 1,000-foot perspective, it sounds very similar. You have to recompile. Minor changes to source code potentially, and it uses capabilities concept, which I think is in Phil C. Cherry is a capability architecture. Early capability architectures such as the CAP computer and Intel IAPX 432 demonstrated secure memory management, but were hindered by performance overheads and complexity. As systems became faster and more complex, vulnerabilities like buffer overflows and use after free errors became widespread. Cherry addresses these challenges with a design intended for modern computing environments. It enforces memory safety and provides secure sharing and isolation to handle increasing software complexity that combat cyber attacks. In the 1970s and 1980s, early capability architecture such as the CAP computer, developed by the University of Cambridge, and the Intel IAPX 432 demonstrated strong security properties. These systems relied on indirection tables to manage capabilities, introducing performance bottlenecks as memory access required multiple lookups. While this approach worked when processes were slow and memory was fast, it became impractical by the mid-1980s as processors became faster and memory access times lagged behind. In 2010, DARPA launched the Clean Slate Design of Resilient Adaptive Secure Host (CRASH) program. That seems like a backronym if I've ever seen one, which tasks participants with redesigning computer systems to improve security. SRI International and the University of Cambridge team revisited capability architectures seeking to address memory safety challenges inherent in conventional designs. Mechanism, that's really what I'm interested in. So what do you got? Memory access with and without Cherry. So without Cherry, what address does this pointer point to? With Cherry, what can I do with this pointer? So you store two. Is this a pointer? What can I do with this pointer? Is this an opaque sealed pointer, and what kind? What range of memory can I use? So in addition to storing the address, you just store all this metadata, and then there's also a thing called a tag, which is probably some type of like table or something. I don't know. Let's see. A cherry system operates at a hardware level by providing a hardware-enforced type, a cherry capability, that authorizes access to memory. This type includes an address and other metadata, such as bounds and permissions. Instructions such as load, stores, and jumps that access memory use one of these types to authorize access, whereas on traditional architecture they would simply use the address. This metadata is stored inline alongside the address in the computer's memory and protected by a tag bit, which is cleared if the capability is tampered with. This informs the computer of which areas of memory can be accessed through a specific operation and how a program can modify or read memory through that operation. This allows cherry systems to catch cases where memory that was outside the bounds of where the program was supposed to read or write to was operated on, associating the metadata with the value used to access memory rather than the memory being accessed. In contrast to a memory management unit, means the hardware can catch cases where a program attempts to access a part of memory that it should have access to while intending to access a different piece of memory. Implementations of cherry systems also include modifications to the default memory allocator, which is a component that defines that a range of addresses should be treated by a program as an object. On a cherry system, it must also communicate this information to the hardware by setting the bounds on the pointer, represented by a cherry capability that is returned. It may also communicate the lifetime to prevent use after free or use after reuse bugs. Depending on the context, cherry systems can be used to enhance compiler level checks, build secure enclaves, or even be used to augment existing instruction architectures. A report by Microsoft in 2019 found that cherry's protections could be used to mitigate over 70% of memory safety issues found in 2019 at the company. Cherry architectures are also designed to be backwards compatible with existing programming languages such as C and C++. A study performed by University of Cambridge researchers found that porting 6 million lines of C and C++ source code to Cherry required changes to 0.026% of the source lines of code. So that's 26 out of 1,000. And they did 6 million. That's still a lot of source code that needs to be changed. 26 lines out of 1,000 would be what? 26 million? No, sorry. 26 out of 1,000. It'd be 26,000 lines of code. I'm doing the arithmetic right there. Let's just use Python. It's 26,000. Should really be able to do this in my head. So it'd be 6 million times 0.00. Where are you at here? So 0.026. I said 26,000. 156,000. Oh, because you have to multiply it by 6. If you take that and divide it by 6, it'd be 26,000, yeah. I was doing by 1 million, because I was just doing order of magnitude. Okay. So, still a lot of source code that needs to be changed there. Limits. The architecture introduces hardware complexity due to the tag bit mechanisms and capability checks needed to enforce memory safety, although optimizing has been implemented to minimize these impacts. The performance trade-offs can vary depending on specific workloads and specific implementations. Further, Cherry needs modifications to both software and hardware ecosystems. Implementations such as Morello allow unmodified binaries to run, but these get no added security benefits. Software must be recompiled or adapted to use Cherry's capability-based model, and hardware makers must incorporate Cherry extensions into their designs. Standardization remains an ongoing effort, while initializations such as the Cherry Alliance and RISC-V standardization aim to establish broader support. The lack of widely accepted industry standards for Cherry features have delayed adoption. Adapting legacy software or retrofitting existing systems to work with Cherry can be challenging, particularly for large and heterogeneous code bases. The difficulty often stems from programming practices used during the software's original development, such as implementing custom memory management, where identifying pointers from integers can be particularly problematic. Implementations. History. I don't care about the history. Is there like a C also? What was the other thing again? Pointer authentication codes. Wait a minute. Oh, it's part of this. An ARM v8.3a architecture introduced a new feature at the hardware level that takes advantage of unused bits in the pointer address space for cryptographically signed pointer addresses using a specially designed tweakable block cipher, which signs the desired value, typically a return address, combined with a local context value, e.g. the stack pointer, before performing a sensitive operation, i.e. returning from the saved pointer. The signature can be checked to detect tampering or usage in the incorrect context, e.g. leveraging a saved return address from an exploit trampoline context. Apple Silicons since A12 have upgraded to ARM v8.3 and use PACs. Linux gained support for pointer authentication within the kernel, and version 5.7, released in 2020, support for user space application was added in 2018. In 2022, researchers at MIT published a side-channel attack against PACs dubbed Pac-Man. So these are all to get away from or mitigate return-oriented programming attacks. we should continue reading. We have a practice problem coming up here. Okay, so we have this diagram here. Start of the heap, we have an unused byte because it's implied that it's the start of the heap. We don't need to know the length of that, I think. That's the way that, no. Organizing the heap with an implicit free list. Allocated blocks are shaded. Okay. Free blocks are unshaded. Headers are labeled with size / blocks. Okay, so first block is unused. That's odd. Not sure why that is. And then we got the size and allocated bit. The allocate bit to indicate whether the block is allocated free. For example, suppose we have an allocated block with a block size of 24 or 0x18 bytes, then its header would be, you add 1 to it basically. Similarly, a free block with a block size of 40 bytes would have a header of 28, and it would just come out as 28. The header is followed by the payload that the application requested when it called malloc. Payload is followed by a chunk of unused padding that can be any size. There are a number of reasons for the padding. For example, the padding might be a part of the allocator strategy for combating external fragmentation, or it might be needed to satisfy the alignment requirement. Given the block format in figure 935, we can organize the heap as a sequence of contiguous allocated and free blocks, as shown in 936. We call this organization an implicit free list because the free blocks are linked implicitly by the size fields of the headers. The allocator can indirectly traverse the entire set of free blocks by traversing all of the blocks in the heap. Notice we need some kind of specially marked end block. In this example, a terminating header with the allocated bit set and a size of 0. Okay, as you'll see in section 9912, setting the allocated bit simplifies the coalescing of free blocks. The advantage of an implicit free list is simplicity. A significant disadvantage is that the cost of any operation that requires a search of the free list, such as placing allocated blocks, will be linear in the total number of allocated and free blocks in the heap. It is important to realize that the system's alignment requirement and the allocator's choice of block format impose a minimum block size on the allocator. No allocated or free block may be smaller than this minimum. For example, if we assume a double word alignment requirement, then the size of each block must be a multiple of 2 words or 8 bytes. Thus, the block format in the figure 935 induces a minimum block size of 2 words. 1 word for the header and another to maintain the alignment requirement. Even if the application were to request a single byte, the allocator would still create a 2-word block. Alright, practice problem 9.6. Let's kill that. Let's go over our problems. Go down here, 9.6. And it's determined the block sizes and header values that would result from the following sequence of malloc requests. Assumptions: the allocator maintains double word alignment and uses implicit free list with the block format from figure 935. Block sizes are rounded up to the nearest multiple of 8 bytes. Okay, let's go ahead and generate our what's this guy here? Markdown table generator. And it's going to be 1, 2, 3, 4, 5 rows and 3 columns. Oops. All right. I have a question about this problem already. So in the lecture, he was talking about using Malloch's API instead of being bytes. Malloch's API would be word sized. I'm guessing he's not doing that in here. I don't see any examples of calling malloc in this text. Here we go. Figure 934 has malloc calls in the diagram, and they're using bytes, as you should. Okay. So let's reread the problem statement because there's some assumptions here that I need to consider. Assumptions: the allocator maintains double word alignment. So double word alignment. And he said something about the word size before. So normally a double word would be 4 bytes, but I think he's saying 8 bytes now would be a double word. So double word alignment would be 8 bytes. And uses an implicit free list with the block format from 935. Block size is going to be 4 bytes, which is the header, and then plus payload plus padding. With 8 bytes. Okay, so that's going to be our block size. Block size are round up to the nearest multiple of 8 bytes, exactly. So malloc 2, you have 2 bytes, and then you have 4 bytes for the header. So that's going to be block size of 8. And you want your block header in hexadecimal. So the block header is going to be the size and whether it's allocated or not. And of course it's going to be allocated because we just called malloc. So this would be, I'm going to just go ahead and do a 0x here. Oops. What the hell happened there? Alright, so malloc 2, block size of 8. So normally it would just be an 8, but then you have to also set the 1 bit, so it's going to be a 9. When we allocate 9 bytes plus the 4 for the header, that's going to be 9, 10, 11, 12, 13, so it's going to be 16. That would make its size equal to 10, and then you have to add a 1 to it. And because the header is always 8 bytes, that means that this has to be 2 nibbles. So I'm going to put a 0 here just to make that explicit. Okay, malloc 15, of course, it's going to be padding. With padding, it's going to be 16, and then the header, which will be 24. So that'll be 1 for 16, and then another 8 will be the hexadecimal of 24, and then we got to add 1, which would be 9. And then finally malloc 20. So obviously 8, 16, 24 would be with the padding, and you have to add another 8, which would be 32. So 32 bytes here. Oh, I assumed 8 for the header. That's my bad. Let's back out of that. So I think some of these results might be wrong. Let's go ahead and redo them. So 2 plus 4 would be 6 rounded up to 8. That's correct. With this one, it's going to be 9 plus 4, 9, 10, 11, 12, 13, 14, 15, 16. So that's correct. 15 plus 4 would be 19. And that's going to be 24 as well. Okay, so I'm still correct. 20 plus 4 would be 24. Would be the size. And then the actual representation here would be, what we got, 8, 16. And then another 8, which would be here. And then a 9 there. I think it'd be the same for both of these. Because 15 and 4 is 19, 20 and 4 is 24. They're going to be the same block size and the same header. Okay, let's check our answers on this one. It's 9, 6. Let's go to the back of the book here. What happened to my bookmark? Did I lose my... Oh, it's over here. Alright. So... that's homework problems. What about the practice problems? At the very back. Okay. 9, 6. Which is here. This problem touches on some core ideas such as alignment requirements, minimum block sizes, and header encodings. The general approach for determining the block size is to round the sum of the requested payload and header sizes to the nearest multiple of the alignment requirement, in this case 8 bytes. For example, block size of malloc 2 is 4 plus 2 is 6 rounded up to 8. Block size for malloc 20 request is 20 plus 4 is 24 rounded up to 24. No need to round up since it's already aligned. So we got 8, 16, 24, 24, 9, 11, 19, 19. Yep. Flawless victory. All right. Placing allocated blocks. When an application requests a block of k bytes, the allocator searches the free list for a free block that is large enough to hold the requested block. The manner in which the allocator performs the search is determined by the placement policy. Some common policies are first fit, next fit, and best fit. First fit searches the free list from the beginning and chooses the first free blocks that fits. Next fit is similar to the first fit, but instead of starting each search at the beginning of the list, it starts each search where the previous search left off. Best fit examines every free block and chooses a free block with the smallest size that fits. An advantage of first fit is that it tends to retain large free blocks at the end of the list. A disadvantage is that it tends to leave splinters of small free blocks towards the beginning of the list, which will increase the search time for larger blocks. Next fit was produced by Donald Knuth as an alternative to first fit, motivated by the idea that if we found a fit in some free block the last time, there is a good chance that we will find a fit the next time in the remainder of the block. Next fit can run significantly faster than first fit, especially in the front of the list becomes littered with many small splinters. However, some studies suggest that next fit suffers from worse memory utilization than first fit. Studies have found that best fit generally enjoys better memory utilization than either first fit or next fit. However, the disadvantage of using best fit with simple free list organizations such as the implicit free list is that it requires an exhaustive search of the heap. Later, we will look at more sophisticated, segregated free list organizations that approximate a best fit policy without an exhaustive search of the heap. Splitting free blocks. Once an allocator has located a free block that fits, it must make another policy decision about how much of the free block to allocate. One option is to use the entire free block, although simple and fast. The main disadvantage is that it should focus on this. Is that it introduces internal fragmentation. If the placement policy tends to produce good fits, then some additional internal fragmentation might be acceptable. However, if the fit is not good, then the allocator will usually opt to split the free blocks into two parts. The first part becomes the allocated block, and the remainder becomes a new free block. Figure 937 shows how the allocator might split the 8-word free block in figure 936 to satisfy an application's request for 3 words of heap memory. So we have this diagram. Splitting a free block to satisfy a 3-word allocation request. Allocated blocks are shaded. Free blocks are unshaded. Headers are labeled with size by allocate. So we're going through, we want to place something in the free area. Then we have to go along and find the area. Oh, the reason why that first block is unused is that the pointer to the actual payload needs to be 2-word aligned in this situation. And that means that the header has to go 1 word behind it, a boundary, a 2-word boundary. So that can't be used then, because you would be putting the header behind here if we use that for payload. And if we did it here, if we had the header here and the payload here, it wouldn't be the payload wouldn't be 2-word aligned or double word aligned. Okay, that makes sense. Getting additional heap memory. What happens if the allocator is unable to find a fit for the requested block? One option is to try to create some larger free blocks by merging, coalescing free blocks that are physically adjacent in memory. However, if this does not yield a sufficiently large block, or if the free blocks are already maximally coalesced, then the allocator asks the kernel for additional heap memory by calling the sbreak function. The allocator transforms the additional memory into one large free block, inserts the block into the free list, and then places the requested block in this new free block. Coalescing free blocks. When the allocator frees an allocated block, there might be other free blocks that are adjacent to the newly freed block. Such adjacent free blocks can cause a phenomenon known as false fragmentation, where there is a lot of available free memory chopped up into small unusable free blocks. For example, figure 338 shows the result of freeing the block that was allocated in figure 937. The result is 2 adjacent free blocks with payloads of 3 words each. As a result, the subsequent request for a payload of 4 words would fail, even though the aggregate size of the 2 free blocks is large enough to satisfy the request. To combat false fragmentation, any practical allocator must merge adjacent free blocks in a process known as coalescing. This raises an important policy decision about when to perform coalescing. An allocator can opt for immediate coalescing by merging any adjacent blocks each time a block is freed, or it can opt for deferred coalescing by waiting to coalesce free blocks at some later time. For this example, the allocator might defer coalescing until some allocation request fails, and then scan the entire heap, coalescing all free blocks. Example of false fragmentation, because we got the 2 freed blocks there that have not been coalesced. Immediate coalescing is straightforward and can be performed in constant time, but with some request patterns it can introduce a form of thrashing where a block is repeatedly coalesced and then split soon after. For example, in figure 398, a repeated pattern of allocating and freeing a 3-word block would induce a lot of unnecessary splitting and coalescing. In our discussion of allocators, we will assume immediate coalescing, but you should be aware that fast allocators often opt for some form of deferred coalescing. Coalescing with boundary tags. How does an allocator implement coalescing? Let's us refer to the block we want to free as the current block. Then coalescing the next free block in memory is straightforward and efficient. The header of the current block points to the header of the next block, which can be checked to determine if the next block is free. If so, its size is simply added to the size of the current header, and the blocks are coalesced in constant time. But how would we coalesce the previous block? Given an implicit free list of blocks with headers, the only option would be to search the entire list, remembering the location of the previous block, until we reach the current block. With an implicit free list, this means that each call to free would require time linear in the size of the heap. Even with more sophisticated free list organizations, the search time would not be constant. Knuth developed a clever and general technique known as boundary tags that allowed for constant time coalescing of the previous block. The idea, which is shown in figure 939, is to add a footer, a boundary tag, at the end of each block, where the footer is a replica of the header. If each block includes such a footer, then the allocator can determine the starting location and status of the previous block by inspecting its footer, which is always 1 word away from the start of the current block. Consider all the cases that can exist when the allocator frees the current block. The previous and next blocks are both allocated. The previous block is allocated and the next block is free. The previous block is free and the next block is allocated. The previous and next blocks are both free. This is a format of heap block that uses a boundary tag. So we got our footer included up there. It's good. Figure 940 shows how we would coalesce. There's 940. Okay, that's a diagram here. How we would coalesce each of the 4 cases. So let's look at that diagram before we read the text. Coalescing with boundary tags, case 1, previous and next allocated case. Okay, I got it. Okay. So we just turn it to free. So single bit change there. Case 2, we turn it to free. We then look at the next block's header. We see it's free. We add its value to we add its size to our size, and we flip our bit to free, which I believe is a 0. Yeah, it's a 0. And then here we have a previous one, so we go back 1 word, we look at that, see it's free, and then what we do is we add our size to the header of the previous block size, and it's already free, so we don't need to flip any bits there. And then case 4, we just do both. In case 1, both adjacent blocks are allocated and thus no coalescing is possible, so the status of the current block is simply changed from allocated to free. In case 2, the current block is merged with the next block, the header of the current block and the footer of the next block are updated with the combined sizes of the current block and next blocks. Oh, I forgot you have to update the footers too. In case 3, the previous block is merged with the current block, the header of the previous block and the footer of the current block are updated with the combined size of the two blocks. In case 4, all of the blocks are merged to form a single free block, with the header of the previous block and the footer of the next block updated with the combined sizes of the 3 blocks. In each case, the coalescing is performed in constant time. The idea of boundary tags is a simple and elegant one that generalizes to many different types of allocators and free list organizations. However, there is a potential disadvantage. Requiring each block to contain both a header and a footer can introduce significant memory overhead. If an application manipulates many small blocks, for example, if a graph application dynamically creates and destroys graph nodes by making repeated calls to malloc and free, and each graph node requires only a couple of words of memory, then the header and the footer will consume half of each allocated block. Fortunately, there is a clever optimization of boundary tags that eliminates the need for a footer in allocated blocks. Recall that when we attempt to coalesce the current block with the previous and next blocks in memory. Recall that when we attempt to coalesce the current block with previous and next blocks in memory, the size field in the footer of the previous block is only needed if the previous block is free. If we were to store the allocated free bit of the previous block in one of the excess low order bits of the current block, then allocated blocks would not need footers, and we could use that extra space for payload. Note, however, that free blocks would still need footers. Well, if that footer is random payload noise, you might look at it and get like a sense that it is free, but then you'd have to check. Yeah, there has to be a check there, I guess. I don't know. I don't like this optimization because I don't understand how you make sure that the payload doesn't influence the integrity of your coalescing. Maybe pull up the lecture part. So this was advanced concepts. I want to go to lecture dynamic basic concepts.
Efficiency metrics. We have two, but a free list where all the blocks were the same, it could be 0, because we know that it's 0. We're going to align on out the allocation. So 1, 2. Given all that we've talked about, so the size of that block, we'd have to walk, starting at the very beginning, and walk the entire heap. So the solution for that is, was proposed by a famous computer scientist, Don Knuth, in 1973. And it's very clever, but very simple. Like all really good ideas, it seems obvious that when you see it, but it turns out to be very clever and a very useful technique. And the idea is just to replicate, for each block, replicate the header block at the end of the block. Okay, so each block now contains a header and a footer, identical header and footer. And then this creates sort of an implicit backwards link that we can use. So now, given some block that we want to free, we know that the size of that block will just be one word previous in memory. So we can just, and it's always a fixed offset, right, of one word. So given given a pointer to the header of this block, we can look one word back to see the size and the allocation status of the previous block. Okay, so that allows us to do that in constant time. And so this footer is sometimes called a boundary tag. I think Knuth called it a boundary tag, but we'll just, or we can call it a footer to be sort of parallel with the notion of a header. But the key thing is that it's just identical size and allocation status. Okay, now so given, yes, question. So the question is, if we want to have a boundary tag, when we allocate a block, do we need to set aside space for it? And the answer is yes. Most of the time, I'll show you one. I'll show you one optimization in a bit.
So that's the
okay. So given
we're looking at.
Given this idea of the boundary tag, and given that we have some allocated block that we want to free, this yellow block. Yes, question. Yeah, well, so the yeah, so just to summarize the question, you need to, when you allocate, when you're looking for blocks that fit, you have to include the size of the header and the boundary tag.
Doesn't that mess up the data line?
It would. Then you'd have to insert padding to get a size, a total block size that's a multiple of a multiple that satisfies your alignment requirement. Sorry? Yeah, I mean, it can, yeah. If you have, the question is, wouldn't that use a lot of memory? And it can, again, it depends on the requests, the request pattern. If the application's requesting lots of small payloads, then it's going to waste a lot of memory. If it's requesting big payloads, not so bad. Okay, so given that we have some block that we want to free, there's 4 cases that we need to consider when coalescing. The case where the next block is allocated and the previous block is free is allocated. The case where the next block is free and the previous block is allocated. Case where the previous block is free and the next block is allocated. And the case where both the previous and next block are free. Okay, so in case 1, where we have our allocated block that we want to free surrounded by 2 allocated blocks, we don't do anything, right? Because you only coalesce free memory. So in this case, we just keep the size of the header and footer stays the same, and we just set the allocation status to free. Now, if the next block is free and the previous block is allocated, what we do is we check the boundary tag of the previous block and we see that it's allocated, so there's nothing to do there. We use the size to check the allocation status of the next block. So we use n to jump to the header of the next block. We see that its allocation status is free, so these 2 blocks need to be coalesced. So we do that by just adding the 2 sizes together to create this larger coalesced block and setting its allocation status to 0. Now, in the case where the previous block is free, again, we check the boundary tag footer when we see that it's free. So in this case, we have to update the size of the header of the old previous block to create this now new larger coalesced block. Okay, and we update the header and the boundary tag footer accordingly. And then in the case where both the previous and the next block are free, we create a single block a single block that's the sum of all three of those sizes. Okay, so is that clear to everybody? Now, as you correctly pointed out, that boundary tags can create additional internal fragmentation, right, because they're not part of payload. So by definition, they're overhead. And so you might ask yourself, are there any cases where you don't need a boundary tag? So which blocks need a boundary tag? Could you get away with, does an allocated block need one? Yeah, if you don't need to coalesce, then you don't need that footer. And what kind of blocks don't you coalesce? Allocated blocks. So maybe we don't need those boundary tag footers on allocated blocks, right? Just on free blocks. But then how are we going to determine that the previous block is allocated or free if an allocated block doesn't have a boundary tag footer? Yes? Sorry? Well, yeah, you would give it one when you free it. But somehow when we're doing coalescing, we need to check somehow that previous block, whether it's allocated or free. Okay? But how does it know whether it's a boundary tag or not? Not sure. No, that's okay. That's okay. Yes. Bingo. You got it. So remember this. Remember because of our alignment, we've got multiple, at least 3 bits, 3 or 4 bits that are always 0. We're only using one of them. So why not use another one to contain the allocation status of the previous block? Okay, so very good. That was right, so the idea, so here's the block that we want to free, and here's its header. And we passed a P to it, and we want to free it. And we've got 1 bit. We know that if we have 8-byte alignment, we know that these are all implicitly 0. So we're using, this is a allocated block that we want to free, so it has an allocation status of 1. And let's use one of these spare bits to indicate the allocation status of the previous block. Okay, so if the previous block is allocated, then this would be a 1. And when we're checking to see whether we need to coalesce, we just check that second allocated bit, the allocated bit of the previous block. And if it's 1, we don't need to know what its size is. Okay, and we don't need to know where that block is because we're not going to coalesce it. Okay, so in that we don't need. So here we don't need a boundary tag for an allocated block. But now if that block is free, it'll have a boundary tag. So we'll check if that block is free. Then the allocation status will indicate free, and then we know we need to coalesce. And we're going to need a boundary tag because we need to know where that block starts. We need to know its size so that we can go back and update this size to include the total coalesced size of those two blocks. So is that clear? Yes. Oh, it's just the allocated bit. So 0 means not allocated, 1 means allocated. Oh, why are those bits why are the bits always 0? Okay. So blocks have to be aligned to 8-byte boundaries. Okay, or payloads have to be aligned to 8-byte boundaries. Okay. That means that blocks have to be, the size of blocks has to be a multiple of 8. Because it's the same thing as when we were doing padding alignment in structs. The next, each block has to be, a size has to be a multiple of 8 so that the block that follows it in memory is aligned properly. Okay? So you guarantee, because of the alignment requirement, you're guaranteed that of 8 or 16, you're guaranteed that the size of the blocks are always multiples of either 8 or 16. Okay, and so because that size is always a multiple of 8 or 16, you're guaranteed that either 3 or 4 bits are all zeros. Okay. Any other questions? Okay, let me summarize then some key policies when implementing an allocator. And I mentioned that the design spaces for these things is really large and really interesting. There's a lot of things a lot of decisions that you have to make about various policies. So the first is the placement policy, where when we're trying to place a free block, when we're trying to place an allocator somewhere in a free block somewhere in the list.
That explained to me exactly how to achieve what he's saying with this optimization. So I'm going to switch back over to here. Okay, determine the minimum block size for each of the following combinations of alignment requirements and block formats. Okay, so this is going to require a table. Let's go ahead and get out of full screen here. Mark down table generator. We need 1, 2, 3, 4, 5 by 1, 2, 3, 4 columns. So 5 rows by 4 columns. And then this is going to be alignment, allocated block, free block. Let's go back over here, fix that, and then minimum block size in bytes. And then here will be single word, header and footer, header and footer, single word. This will be header but no footer. This will be header and footer. This will be double word, header and footer, header and footer, double word, header but no footer, header and footer. Alright, so then we do generate, copy to clipboard, do a 9.7 probably, I'm gonna guess. And then in here, it says determine the minimum block size for each of the following combinations of alignment requirements and block formats Assumptions: implicit free list, zero size payloads are not allowed, and headers and footers are stored in 4-byte words. Okay. So that'd be 8 bytes for this guy. And then a single word would be 4. So it'd be 8, 9, 10, 11, 12. But you also need the footer. Well, let's look at it. So we always have a header, which is going to be 4 bytes. And then you have payload. And then you have padding. And then you have footer for payload n, padding, question mark, footer for, but with an asterisk because it could be optional. It could fit into the padding or the payload. So right off, we need 4. So when we have a single word, which is going to be another 4, that means that it would have 4 plus 4, which would be 8. We meet our alignment requirement, which is 8, right? Oh no, the alignment is a single word here. But 8 would align with that. And then no padding. And then the footer can be stored in the payload location. So that's going to be an 8. A single word header but no footer. Sorry, I'm confused here what they mean by this. Let's reread the thing. Determine the minimum block size for each of the following combinations of alignment requirements and block formats. Okay, so this gives us actually header and footer in the free block. The allocated block also has a footer, so this would be wrong then. So we have a header for, payload for, so alignment, allocated block, free block. So let's take the allocated block. It's going to be the bounding because all of these are potentially smaller. These are always going to be larger. Free blocks are always going to be contain a header and footer, and the footer is going to overlap. Okay, let's just take it one by one. So we have a header, which is 4 bytes, a payload, which is non-zero, so it could be 1 byte. So header 4, payload 1, padding, whatever's necessary, and then the footer, which is also 4. So that's going to be 9 bytes, which will require us to have 3 here. So that's going to be 12. Now we'll do the next one. Let's do this down here. Makes it a little bit easier to keep track of things. So we have a header again 4. Oh, so sorry. That's got to be header and footer. And then free block, header and footer as well. Okay. This one, header but no footer. So we have our header. Our footer can occupy the block, the payload section. So header but no footer. Single word. Payload 1. So that's 4, 5. Then padding's gonna be 3. So 6, 7, 8. That'd be 8 here. All right. Header and footer. So header is going to be 4. We have to be offset appropriately, but I don't think it's going to impact the size of the block. 1 byte payload, and then we have some amount of padding, and then the footer is going to be 4 as well. So we have 4. This is going to be on the boundaries. This has to be 7. And then another 4. So 8, 9, 10, 11, 12. So that's going to be 16. Yep. 16. And then this one, double word. We're going to have a 4 byte header. Payload is 1 byte. Padding is some amount. Footer is going to be 0. Then we have 4, 5. This could be 3. So it'd be 8. Yeah, I think that's the answer. 12, 8, 16, 8. Let's take a look at the back of the chapter. Okay, 12, 8, 16, 8. Yep. And we'll read the text here. The minimum block size can have a significant effect on internal fragmentation. Thus, it's good to understand a minimum block size associated with different allocator designs and alignment requirements. The tricky part is to realize that the same block can be allocated or free at different points in time. Thus, the minimum block size is the maximum of the minimum allocated block size and the minimum free block size. For example, in the last subproblem, the minimum allocated block size is a 4 byte header and a 1 byte payload rounded up to 8 bytes. The minimum free block size is a 4 byte header and a 4 byte footer, which is already a multiple of 8 and doesn't need to be rounded. So the minimum block size for this allocator is 8 bytes. Okay, got that correct. Let's move on to the next page. Here we go. Putting it all together. Implementing a simple allocator. Building an allocator is a challenging task. The design space is large with numerous alternatives for block format and free list format, as well as placement, splitting, and coalescing policies. Another challenge is that you are often forced to program outside the safe, familiar confines of the type system, relying on the error-prone pointer casting and pointer arithmetic that is typical of low-level systems programming. While allocators do not require enormous amounts of code, they are subtle and unforgiving. Students familiar with high-level languages such as C++ or Java often hit a conceptual wall when they first encounter this style of programming. To help you clear this hurdle, we will work through the implementation of a simple allocator based on the implicit free list with immediate boundary tag coalescing. The maximum block size is 2 to the power 32 or 4 gigabytes. The code is 64-bit clean, running without modification in 32-bit or 64-bit process. General allocator design. Our allocator uses a model of the memory system provided by the memlib.c package shown in figure 941. The purpose of the model is to allow us to run our allocator without interfering with the existing system level malloc package. The meminit function models the virtual memory available to the heap as a large double word aligned array of bytes. The bytes between memheap and membreak represent allocated virtual memory. The bytes following mem break represent unallocated virtual memory. The allocator requests additional heap memory by calling the mem sbreak function, which has the same interface as the system's sbreak function, as well as the same semantics, except that it rejects requests to shrink the heap. The allocator itself is contained in a source file mm.c that users can compile and link into their applications. The allocator exports 3 functions to applications. So we got our init, our malloc, and our free. The init function initializes the allocator, returning 0 if successful and -1 otherwise. The malloc and free functions have the same interfaces and semantics of their system counterparts. The allocator uses the block format shown in figure 939. The minimum block size is 16 bytes, probably because 64-bit header and footer. The free list is organized as an implicit free list with a variant form shown in figure 942. All right, let's take a look at it, at the code here. So we got private global variables, static char mem heap points to the first byte of the heap, mem break points to the last byte of the heap +1. Yeah, it makes sense. It's the first byte that's not in the heap. And then mem max adder, max legal heap address +1. Okay. Initialize memory model, memory system model here. You got mem init. So we say, hey, malloc up to max heap. And then our break is going to be at the heap initially. And then our max adder is going to be mem heap plus the max heap. We don't want to exceed that. And then we have an sbreak. Simple model for sbreak function extends the heap by increment bytes and returns the start address of the new area. In this model, the heap cannot be shrunk. So we just so we have this global mem break. We set it to the old value. We're going to return the old value when we're done here. And then we do a conditional check and then some error handling code. Otherwise, we just add the increment to the memory break. So we say, hey, if increment is less than 0, well, that's not good. You can't shrink the break on this implementation. So if that happens, or the current break plus the increment is greater than the max address that we recorded in the init, then we got a problem. And we need to say, hey, the error knows e no mem. We're going to printf out error, mem sbreak failed, ran out of memory, and return a -1 from the sbreak. Alright, pretty straightforward. Let's check our calendar real quick. So we got 15 minutes here. Wondering how much I can get into this. Okay. Before we go any further, I am going to just take my lunch break a little bit early here. I need to take a bio break and I need to get lunch and cardio. So we'll shorten this session a little bit and we'll start the break early. So this will start at 1:15 to 5. Okay, cool. I'll take a break there then, and when I come back, we'll continue reading about their implementation of this implicit free list memory allocator. Cool. All right, I'll be on later. Bye.